Next, let us try an example to design for slabs using the same key plan that we did previously. It is given that the GK and QK are 4.6 kN per meter square and 2.5 kN per meter square respectively. And it is assumed that the GK given, which is 4.6 kN per meter square, is inclusive of the self-weight of the slab. From the key plan, there are a total of 8 panels, and there is a void at the center of the building structure. The thickness of the slab is stated, which is equals to 150 mm. The dimensions are given. The details given in the questions include the concrete strength FCK equals to 30, specified yield strength FYK equals to 500, concrete cover 30 mm, maximum aggregate size 20 mm, and the reinforcement bar H10 are to be used. Now let us look at the question. The question asks us to determine the largest moment acting on slab BC12 and identify the locations of the largest moment. First, you need to know which slab is BC12, refers to the key plan. BC12 is this slab. Based on the ratio, it is two-way slab. The thickness of the slab is 150. The question asks us to determine the moment acting on the slab. For a typical two-way slab, in order to get the moment, you will need to refer to British Standard at 110 to get the coefficients for bending moment. The table that we are referring to is table 3.14 in British Standard at 110. In order to get the right coefficient, you must first know the classifications of the slab. We did the classifications in our previous example while designing for the beams. Referring to this slab here, you know that these two edges are continuous and these two edges are discontinuous. The discontinuous edges are the short edges. Therefore, you know that this will be two short edges discontinuous. Therefore, from table 3.14, you should look for two short edges discontinuous. There are two coefficients here, the short span coefficients and the long span coefficient. The short span coefficients refers to the coefficients here, which is in the directions of the short span, whereas the long span coefficient refers to the coefficients here, which is in the directions of the long span. Now it can be quite confusing which coefficients is for which, especially when come to the final exam. Sometimes we got panic. Probably we could do it in some other times, but sometimes when come to the final exam, we are lacking the confidence. Which coefficients is for which span? Let's say if you do not know, don't panic first. You will refer to the slab, two short edge discontinuous. You will see in one direction there will be negative moment at the continuous edge and positive moment at the midspan. Whereas in another directions, there is no negative moment, but there is positive moment at the midspan. Now if you come back to this slab here, there will always be negative moment at the continuous edge, and there always be positive moment at the midspan. That means regardless what conditions or what direction, there will always be positive moment at the midspan. Now you will have to look at the negative moment to decide which edge that you are referring to. Continuous edge will have moment, whereas discontinuous edge is without moment. By looking at the coefficients here, when there is a number for the coefficients, that means there will be moment. Whereas when there is no number here, that means there won't be any moment. Therefore, when come back to this slab here, you know that the coefficient here at the shorter span are meant for this, and this. Whereas the coefficients at the longer span, there is no moment at the support, then you know that you are talking about these three. 0 moment here and 0 moment here. Identifying which span is which may be easy for this kind of slab. What if the slab that you are dealing with is something like this or something like this? Now you cannot use this dash for you to identify which coefficients is used for which conditions. And now you just happen that lacking confidence, not sure where these coefficients are referring to. Under such circumstances, don't panic first. In order for you to know where the coefficient should be placed, you can mimic the layout of the slab. Use the same dimensions for that particular slab that you are designing, and then preset the conditions. As is, it is too short edge discontinuous or too long edge discontinuous. Then you do the same process, identifying where are the continuous and the discontinuous edges. Is it in the shorter span or the longer span? Once you have concluded which coefficients go for which edge, then you use back the coefficients given in that particular classifications of the slab. Coming back to this slab, the shorter span, it will be this one. Too short edge discontinuous. The coefficients are given here. There will be coefficients for the continuous edge and the coefficients for the midspan. The continuous edge coefficients shall be applied at the continuous edges. As for the midspan coefficients, that will be here. Same goes to the coefficients for the longer span. The two discontinuous edges are without any moment. The coefficient here, it will be for the midspan in these directions. Now, out of so many numbers here, which number should be used? This refers to the Ly per Lx ratio. From the key plan, the Ly is 5.6 meter and the Lx is 4 meter. Take 5.6 meter divided by 4 meters, you get your Ly per Lx equals to 1.4. The Ly per Lx ratio is less than 2.0. That means it's going to be two-way slab. With that, take the Ly per Lx ratio equals to 1.4, refers to the classifications of too short edge discontinuous That means you get these coefficients: 0.06, 0.045, and 0.034. 0.06 is for the continuous edge, and 0.045 it will be for the midspan. That means you expect this going to be 0.06 here also, and at the midspan it will be 0.045. As for the longer span, the midspan it will be 0.034. That means here will be 0, 0, and 0.034. Theoretically, for this slab alone, you will need to design at least 3 moments. Each coefficient will give you a moment. There are several ways to do it. You can choose to design every single moment, provide the reinforcement accordingly, depending on the magnitude of the moment, so that the slab can pass. However, in practice, normally we design for the largest moment and apply to all. Why is it so? First, you know a typical slab. It is a large panel, probably the largest structural element in a skeleton frame system of a RC structure. In terms of the amount of concrete relative to the load, it is more than enough. In other words, you have plenty of materials for the slab to carry a little amount of load. Now, if you design in accordance to the moment calculated here, although the moment value may differ slightly, it is most likely that the amount of reinforcement required is more or less somewhere of the minimum AS, since you have a lot of concrete in the panel. This is especially when a member is subjected to typical loading, as stipulated in Eurocode 1. For typical residential or commercial applications, the QKs are relatively low, barely exceeds 3 kilonewtons per meter square. Therefore, it is no point for you to design for the moment separate. Another reasons for not designing for different moments, it will be due to the practical considerations. You have to consider the supervisions process done by the site engineer. In order to make the supervisions process easier, the designer tends to simplify the design with as minimum as possible the variety in terms of the design outcome. The more variety in terms of the arrangements of the reinforcement, more time will be spent while supervising the constructions of the structural element. Therefore, normally in the industrial practices, most of the slab will have similar amount of reinforcement, so that they don't easily mess up dealing with different arrangements of the reinforcement for different slabs. Third, for a typical final exam questions, normally assessments is done on certain aspect only once. Due to the time constraint given to the student to solve the exam questions, and due to the large scope covered by reinforced concrete design 1, a typical final exam questions will not ask you to design different moments at different locations of the slab differently. Most likely the questions will ask you to design for the most critical moment and apply to all, or sometimes the exam questions will specify which part of the slab is to be designed. It can be at the midspan of the longer span, or it can be some other places. Just that you have to read carefully the questions. Which part of the slab is to be designed? With that, coming back to the question. The questions asks us to determine the largest moment acting on the slab, and then identify its location. Based on the ratio given, the largest moment it will be associated with the largest ratio, which happens at the negative moment at the continuous edge. That means the critical moment will happen here. Then you're going to expect the design later will focus here, and based on the amount of reinforcement provided, you're going to apply all throughout the entire slab. This is more realistic for the assessment in final exam. Now that we have identified the coefficients, which is 0.06, that is the largest value of the three. Next, we will use these coefficients to determine the moment. Refers to the British standard. The moment of the slab is given by the equation here. The coefficients will refer to table 3.14, which is the table that we were referring just now. Having the beta of 10, you will need the Lx. The Ls refers to the shortest span, which is 4 meters. You will have to be careful with the equations. Don't mess up the equations for the moment with the equations for the shear. The equations for the moment have the Ls power of 2, whereas the equations for the shear, your Ls is without power of 2. These are the common mistakes by the students. Be careful, don't get them mixed up. Next, it will be the design load. To determine the design load, you will need to know the purpose of this process. The process now is to determine the moment, so that you can design for the reinforcement. When you deal with the moment and shear, that means we are talking about the ultimate limit state. For the ultimate limit state, Eurocode, the factor of safety for GK is 1.35 and factor of safety for QK is 1.5. Although you adopt the coefficients from the British standard, your factor of safety used it will be in accordance to the Eurocode. The factor of safety for British standard it will be 1.4 GK and 1.6 QK. We are not using the British standard to design the reinforced concrete slab. British standards has already been obsolete in the applications of reinforced concrete structures. Now the next question it will be, why are we using the coefficients from the British standard since it is already obsolete? The reason being here is Eurocode do not provide any guideline in analyzing the moment and shear on a slab. When there is no guideline provided by the Eurocode, you will need to analyze the load acting on the slab by yourself. This is provided that you really know how to analyze the load on the slab. Now, if you do not know how to do it, then you may refer to the guideline given by the British standard. At least this is a systematic method that you may use to determine the loads acting on the slab. Now get your design load. Given the GK is 4.6 and QK is 2.5, substitute into the equations, you get your design load 9.96 kilonewton per meter square. Now you have the coefficients, you have the design load, and you have the shorter span. Substitute the value, you get your design moment 9.56 kilonewton meter, and you know that the largest moment occurred at the support of the shorter span.